Okay, looks like we are live. We'll give everyone a few seconds here to trickle in, but want to welcome everyone. Thank you for joining. My name is Harrison Burt. I'm the Director of Fundraising at StartEngine. I'm joined today by Charles Yeomans, the Chairman and CEO of Atombeam, and also by Rear Admiral Boris Becker. Admiral Becker, for a little background, was the former commander of the Naval Information Warfare Systems Command. In that role, he oversaw an 11,000-person global organization responsible for the Navy's digital, cyber, and space systems. Since retiring from the Navy, he's served as a senior advisor, C-level executive, and board member in space and information technology companies, one of those being Atombeam, where he is on the board. So we're welcoming Charles and Admiral Becker here today to talk about Atombeam and specifically some of their technology applications in defense and in intelligence. And Charles, I believe you have a few slides you're going to show us to start, just to bring everyone up to speed on the technology and your current raise, and then we'll dive into some Q&A.
Yeah, that's right. Thanks, Harrison. So just really quickly here, quick introduction. So I'm Charles Yeomans, CEO and one of the founders of Atombeam. And what I want to do in this is give everybody a chance to take a look at what we do, and then focus more on Admiral Becker is going to give us some background on how he sees what we do and how it could work and everything in for DoD and in space. Admiral Becker was also a very high-level guy at the NRO and oversaw satellite programs there. So I think between those things, we can give you a pretty good overview of sort of a quick rundown of here's the tech that we have, and then talk about the specifics with respect to DoD, and then we can open it up for some questions. So that's the goal. So without further ado, I'm going to share some slides, and we will get going. Hang on one sec. All right. Oops, wrong slide. Okay. So let's see. So here we go. Darn it. Nope. All right. So just really quickly, as Harrison was saying, Admiral Becker was a two-star admiral and commanded one of the most important systems commands in the Navy. Navy has a series of systems commands that oversee things like NAV-C, which oversees the surface ships, and NAV-Air, which oversees the aircraft. All the systems that are involved. It's a highly complex and very large organization that he was managing. Let's now dig in a little bit and talk about what do we do and why do we do this. So really quickly on what we're addressing. It's like there's a massive amount of data. There's like this year there's 181 zettabytes according to IDC is going to get generated. How do you deal with all that? It's an enormous amount. It's hard to express, how big it is, but hardly any of it actually gets used for anything. And a lot of that is because you can't move it. It gets generated in some little sensor somewhere, and then hardly any of it actually gets somewhere where it actually gets used for anything, like under 1% of it. So what do? You have to do two things. One, you got to send it more efficiently, and that's part of what we do. And the other big thing is you have to be able to analyze it out on the edge instead of sending it to some giant data center, in Memphis, Tennessee or something. And then the other big thing is, with AI, to talk about our AI briefly, what's the problem with LLMs and all the other kinds of AI? Well, they don't learn anything. They have to be retrained. They use an enormous amount of power. The amount of power that these AI systems are using now is ginormous and getting more so. And then also hallucinations are a huge issue, as anybody who's used these LLMs can tell you. And so what we do really is we got two things that address all this. One thing that's an actual product that's released and all that stuff is NURPAC. And what NURPAC does is it quadruples bandwidth in effect on average. And it does that by changing out the contents of messages for code words. And so it takes a message, takes a file, and swaps out the contents with representations out of a code book. And it can do this really fast. It does it so fast, a few microseconds, and then you can do an incredible amount of things with that. You can effectively quadruple the amount of bandwidth, and you don't have to change any hardware to do that. To change it to quadruple bandwidth with hardware depends on the situation, of course, but it could be billions of dollars. And NURPAC can do it a lot cheaper than that. And then the other thing we're going to talk about briefly is the PCM, the Persistent Cognitive Machine, which is our, now still in development, just to be clear, but our AI. It uses, instead of using a LLM type neural nets, it uses high dimensional geometry, which is a brand new idea. And I can say that with confidence because we got patents, like we're ripping out the patents and getting granted the patents, alive the patents. And the cool thing is it learns, unlike LLMs. It'll explore things. It'll learn through experience. It doesn't have hardly any, we believe it will have very few hallucinations. We also believe it will have dramatically lower computational costs. And these instances of it, that is to say different, users with their own PCM instances will be able to talk to each other and learn from each other. Federate, that's what that's called. And then we think that also, and this is again a under development project, we think that the memory will stabilize at no more than 250 gigabytes. And that would be a big organization over a long period of time. So an incredible reduction in the amount of data it needs, the amount of storage it needs, how it can work on the edge, because it doesn't have all that. So neat for all that that an LLM has. So Al-Hamrani, just really quickly on NURPAC, Al-Hamrani is using it right now to move data around. It's all this point of sale data from 50,000 locations, getting 78% reduction. They're happy as can be and reselling for us. Viasat's using it right now, and the Space Force is using it also, or actually they're testing it to use it. So just really quickly, what is the difference between what we're talking about here between a PCM and an LLM? So a neural net is the thing you see on the left. That is a bunch of things, little nodes that are connected to a bunch of other nodes, and they have different weights in each node. That's the core part of how a neural net works. And that's what neural nets are what LLMs are based on. Entirely different idea with PCM. It's using geometry and concentrations of thought in these different areas, and the communication between them is in the trajectory of thought between these different areas is what makes PCM tick. That is the core part of it. And I can talk about this a little bit because we have enough patents now. So just really quickly, why is this a big deal right now? Well, if you look at the growth for NURPAC and the amount of data, it's a lot. There's a big need for something that helps move this data around. And that is especially true over satellites, which are increasingly an important place where data moves. And then the PCM, I don't think I have to tell anybody that there's a crisis right now because there is simply not enough power for these LLMs to continue to get bigger and bigger and bigger, where are you going to get the power? And power, you can't just snap your fingers and make it happen. It takes years to get more power in the system. And the U.S. has grown its power, its power grid by maybe 1% a year. And now we're talking like we need like 10% a year or 5% a year, a lot. How do you get that? Well, you can't. And then also, the biggest problem with LLMs is they don't learn. We believe that PCM will be able to learn. We've seen it in early development part of the project. In early development. Hardly any power comparatively, and the size dramatically, hugely less. And so that puts us in a position where we have a huge amount of market opportunity. If you look at these prospective markets. Now, who the hell knows what it really is? This is what we got from various sources, including some AI ourselves. We get awards like every time we get entered into an award, we win. It seems like. I mean, I can't remember the last time we didn't win one. I think we just won another one recently. It isn't even on here. We're up to 345 patents, including 198 pending and 145 issued or allowed. We are, our position with respect to NERPAC is basically there aren't any competitors, because unless you have an opportunity to use compression and you're okay with the latency and you're okay with the extra compute you need, etc., compared to NERPAC, there just really isn't any alternatives. Now with PCM, totally different story, right? I mean, like OpenAI, Anthropic, all those guys, they all have AIs, but we think we have a giant leg up over them. We have a lot of serious dudes involved in this thing, and ladies, of course, women. So we have a really powerhouse group of people doing all this with us. So just to sum up here, we have transformational technologies here, two foundational technologies, and to have two is really amazing. And so when you think about, okay, what if something doesn't work? Well, okay, we have two, but I think more of it in terms of like, NERPAC's a proven product. It's a real thing. And we're coming out with an on-prem version that a lot of people know about and we've mentioned before. And we think that is going to sell huge because we've got, a nice pipeline behind that. And on PCM, the amount of interest we're getting, people are, the big companies are seeing our patents come out, and we're getting calls from people whose names you would recognize. So that being said, that's the quick tour. And so what I'd like to do is shift gears and move over to talk about some DoD applications of these technologies, and in particular ask Admiral Becker for what his thoughts are. So first is Admiral Becker, feel free to just talk if you like. Particularly interested in, sort of how you see, with respect to, you could take NERPAC first, how you see this opportunity to reduce the size of the data that moves in a few microseconds, which effectively quadruples the bandwidth for data links and all kinds of things. How do you see that as important for the Navy, for maritime in general?
For Charles, thanks for inviting me along on this journey, and appreciate the time today to talk a little bit about NERPAC and PCM and about Atombeam. Second thing is a caution, never give a naval aviator an open mic unless you really got a way to pull the plug. So I'll try to keep my comments brief and on target. If I start talking rings and watches, you can feel free to kill the video.
Right.
Where I see this, Charles, is and the reason I'm part of the team and on the board is because I think it really is one of those technologies that fits in the category of a term that is often applied and mostly misused. I think this is game changing because of what the effect of NURPAC on data flows can be. It can have an outsized impact on our most critical resource and the flow of our most critical resource, feeding into our most critical systems. That is information feeding into command and control. The information that is the raw material that feeds into the process that is command and control. There have been different descriptions of how to exercise command and control and how to win through decision making, but one of the terms that is pretty well understood now and often talked about is the OODA loop, right? The observe, orient, decide, and act. The OODA loop comes from some studies and work done by a very famous Air Force aviator, Colonel Boyd, and energy management and whatnot. But anyway, this idea of the OODA loop and getting inside an adversary's OODA loop is critical. Well, the way you do that is the way you can outthink an adversary. Part of that is having information at volume and information at speed. And we have created systems that can crank up data, right? We can create data, we can create zettabytes of data. But where are they going to go and how are they going to get there? Even in today's growing capabilities of almost ubiquitous comms, you might say, well, how can I be starved for communication systems? I've got, Starlink, or pick your architecture. But that's I think oversimplifying the problem. So when we start talking about the amount of data that's available, the amount of data that's available about machines talking to machines, i.e. systems talking to systems, there is really an overwhelming amount of information. Why all that introductory commentary? It's because what NURPAC delivers is a way to move those data into systems today at speed and capacity that we don't have. So if you move 2 or 3 or 4 times the amount of information you have now, you can be that much more perceptive with your sensors about whatever system it is you're measuring. And that perceptivity, that sensitivity, that volume of information is what can give decision makers a leg up in that OODA loop. So there's kind of a long-winded introduction to this idea of how NURPAC, as a way to accelerate the flow of information, is a way to sharpen the edge of decision making and give us an advantage that we so desperately need.
All right, thanks. And could you get specific in terms of, without obviously getting classified, but specific with respect to what's the experience of a warfighter with NURPAC enabled versus not NURPAC enabled in whatever situation you like, aircraft or on the ground or on a ship, whatever?
I'll use a kind of a dual use case example, if you will, and that's part of the commercial TAM, the commercial total addressable market that I see as being very applicable to NURPAC's capabilities, and that's logistics. As we collect data on the functioning of machinery or other parts, e.g. even network performance, those data collect into systems and then can be used to understand the performance of systems, whether that's performance of machinery or status of logistics. All the data about the data about the machinery, the data about the parts, right? All of those metadata are really important because in a world, for instance, in the commercial world of just-in-time inventory, the sooner I know that a shelf is empty, the faster I can plan to refill that shelf, right? That's a very simplified example. Well, make it very applicable, right? When I start to see that a piece of heavy machinery is approaching either an operational limiting condition or a part statistic that something tells me that our part's going to fail, I can make sure that that part is available so that when the machinery does need to be taken down and that part replaced, the part's available. That's all science and practice and state-of-the-shelf sort of operating procedures today. What NORPAC does, though, is allows us to be, what, 2, 3, 4 times as sensitive. So to throw a term around, right, I can increase my sampling rate, I can increase my Nyquist rate to shorten the distance that I'm measuring things, to shorten the time delay or the time lag for those sensors to take important information. And suddenly I'm that much more precise. Well, suddenly if I'm that much more precise, how much more finely tuned can the management of those systems be? And again, I'll put it in context of dual use technology. Telemetry for proliferated architectures. Once upon a time, I had the privilege to deliver space-based capabilities for the Department of Defense and others. What you see behind me there is a launch of a communication satellite that went out to 22,000 miles. Don't get a lot of chance to go and fix it. But if I could be 4 times as perceptive as to when something's going to go wrong, I could start early to prepare changes that I need to make sure that the system stays up and running and stays in operations. Now, that's important for the warfighter. The same concept plays in the commercial market where I can now be ready to keep something in operations, whether it's a refinery, a pump, you pick it. I don't have operational downtime that I might otherwise have. That translates directly either to avoiding cost or adding revenue. And in the DoD terms, that's adding mission or adding lethality or adding survivability and resiliency. These are critical capabilities for our warfighters.
Great, thank you. So thinking about it a little more, like, okay, let's switch over and talk a little about PCM and get into that discussion, because I can see there's some of these are popping up here that, and maybe you could address, there's a couple of questions that have come in directly with, related to the Navy and DoD generally, like, why hasn't DoD gone fully yet? Do you expect phase 3 contracts in their future? And can you speak to how much R&D the Navy is providing? So far, they're not, but we have thoughts on that are specific, and lots of conversations going that I think will bear some fruit here. I have, as I think Admiral, we've talked in the past about Link 16 in particular and so forth. So I think if we could talk about like sort of like big picture, talk about PCM, talk about where that could fit and how you think this command center of the future, whatever you think is sort of like an interesting topic that people want to hear about with respect to that, and particularly with reference to the Navy.
Sure, Charles, thanks. Let's start with buzzword bingo, right? We could talk about AI, we could talk about 3D printing, we could talk about blockchain, right? Just throw some buzzwords out there, mix them all together, get some kind of souffle, bake it up, and here you go. That's not what's going on here. Right? What is what the folks at Atombeam have come up with and are developing at speed is just different. It's different and it's powerful. And it's not just me saying it's different. If you look at the time lag between submission and grant of patents, it's accelerating. So folks who do this for a living are saying, yeah, this is novel, this is new, here's a patent. I have never seen patents come in this quickly. So it's new, it's different, and it's not just another AI play, it's just another buzzword. Listen, AI is not new itself, right? The math behind AI has been around for decades, literally decades, multiple decades, right? 20 plus years ago, I was working with an engineer who was applying a backprop neural net to do some route planning. That was pretty whiz bang at the time. So the idea is not new. but the concept of how PCM works is new and different. And what it, well, I'd like to say I could explain it in terms that a mathematician would understand, but I'd be back to just telling stories with rings and watches, right? There I was. I couldn't tell you the math behind it, but I can tell you the concept behind it. And the concept behind it is almost like folding space. It's folding reasoning space in a way the large language models do not do right now. A large language model is very powerful. And when you add LLMs and the structure of LLMs to today's compute and store technology, well, that's why we have this huge revolution in how AI can assist us. I use AI services to do a variety of things, as to many of you on this call right now. We did not have that ability even 5 years ago. So if you think about that leap from, say, 5 years to today, and the commercial availability and productivity of AI, whether it's making cat memes or solving difficult financial transaction problems or preparing for something very difficult, we understand that and we understand the impact. But those are with models that are, in essence, static. You feed in a lot of learning, which is one of the expenses of large learning models, right? You have to have the data that feed that understanding. And then an LLM will use all that information and provide a very detailed analysis and answer. And then while there is some crossover between the discussions, ultimately an LLM resets and it goes back and starts again. That's not what PCM does. PCM actually learns from operations and is continually sharpening, if you will, its own understanding and creating further understanding. It does this in a way that, as I said earlier, it folds logical space, if you will, and creates pathways that either are very simple and like water, falling down the shortest path. That's the speed with which you can come up with an analysis. Or if it doesn't quite add up, right, it's a longer distance, it takes longer to wonder, like, well, why those two things don't really connect? And I haven't figured out why they should connect yet. So I'll investigate more. That's not how LLMs work. That's how PCM works. And so it gives it a speed. It also gives it a volume that LLMs don't have. And we've seen this in application of when we apply PCM to, well, let's see, let me put it in context. I'm a Star Trek fan, OG Star Trek, right? I learned a lot of my leadership lessons from Good and Other, from 3 seasons of the most forward-leaning science fiction show probably ever produced. Big fan. If you think about the computer, where they ask the computer questions, working, which was actually the voice of Gene Roddenberry's wife. Little Star Trek trivia for you. That's today's AI machine. PCM is more like data from TNG, except instead of walking around and having some, android-looking skin, it's more like in the background, talking to a sentient being and reasoning and getting reasoning back, and a learning sentient being. That's the difference, right? PCM, LLMs, walking around data, lookup machine behind the scenes from the 1960s version. I'll stop there because I think I kind of really lost some folks, but I'm pretty excited about what PCM could do today and where it's going to go.
Yeah, I mean, I have to agree. I mean, the big thing about PCM is it's small, and so it can be in a local thing, like sitting in an airplane, on a ship, even on a drone, and it can be learning something right there, learning and generalizing. So the big thing about PCM that is hard to get your head around, but it's an important distinction, is to think about it this way. So lately, LLMs have started a process whereby they can reference earlier context windows, earlier discussions, chats you've had. And so that's sort of like memory. And it's like, but it's really like a database kind of access of historical discussions. But that's a lot different than actually learning something, changing the internal structure of the LLM, which it doesn't do. All it's doing is checking back on an earlier conversation. Now, the big distinction here with PCM is that picture I showed with those things that move around, those little dots that represent thoughts. Those are actually moving and going over those curvatures. And the curvature, in part, is describing what the thought is about. And so when it looks at that curvature, it might say, as I don't know, Becker was saying, between those things, it might be a bit of a stretch. How do you ever associate, golden retrievers with nuclear physics? I mean, probably not, but maybe I need to at least check and so forth. And so if you think about why an LLM hallucinates, is because a statistical model, and it's taking percentage chances that the next word is this. 60% chance it's that, and so I'm going to go with that. And it's 40% for this, and I'm going to go with that. And so sometimes it'll just go, off on some direction because it chose the wrong percentage thing, and now it's running off, saying, yes, dogs are some of the best nuclear physicists ever. But it's all because it's a statistical model, whereas PCM is solely based on, it thinks more like a human in the sense that, does this make sense? It's hard to translate it. I mean, and I don't understand the math either. The math is exotic. It's really more like physics, more like it's more like general relativity and the curvature of space-time. And that's a description. It's not what it's doing, but it's a description of what it's like. And so that, how gravity distorts space-time is a close representation of how the internals of the PCM operate. And so how that translates into cognition is a difficult thing to explain, but it's sort of like this. If you think about it as you're walking down, so you want to go from here to there, and here to there is a jungle, and you have to bushwhack your way through the thing, and that takes a lot more effort, and that translates to a lot more compute because the dogs and the golden retrievers and nuclear physics really relate. And so you got to beat through this bush here to get to it and figure out, okay. And then after a while, you transverse that same thought pattern because now it's come up again and again and again. And it turns out, well, maybe there is a connection between dogs and nuclear physics. And by then, the path is kind of worn in and it becomes compressed. It becomes much more knowable. And so on that basis, you get this track between these two things, that is the trajectory of the thought, and it becomes an established thing, or not, where it says, no, that's ridiculous. Dogs don't know anything about nuclear physics, and just leave that one alone, and then the path gets grown over again, and boom, you never touch it again. That's the interior of the PCM, and it's very hard to understand it. And I mean, I gotta tell you that neural nets are hard enough, but this is even harder. So anyway, so now anyway, so I don't want to like dwell on the PCM too much, just to emphasize it's in development. It's got serious legs, we believe, and it's going to be a big deal. But let's talk about specifics with respect to how, if you're a warfighter on the ground, or you're driving your F-35, and the F-35 generates gigabits per second of information. And right now, if you want to communicate with another F-35, you can share a lot of that information that's flying along with you in a flight. But if you want to share it with basically anybody else, you got to use Link 16. And Link 16 is 1980s technology. It's 2530 kbps, really slow. How do you share that? And so it becomes a big issue. And how does that guy, and Admiral Becker was describing it very helpfully for us here, that the experience he's getting in this airplane when he's communicating with his carrier, when he's communicating with the tanker or whatever, all that has to be done with dramatically less information flow than is possible. And so the data rate he has, and therefore the amount of information he's got to work with and this aircraft has to work with, is a hugely less, which means he may not be able to be as accurate in targeting. He may not be able to, as accurately locate whatever he's seeking to locate, for example. And so the reality is, with NERPAC integrated into these systems, especially when you're talking satellites, which is extremely limited bandwidth, we can heavily influence the success, the potential success of that guy in that F-35 or F-16 or whatever is out there, or someone in a tank, or even Link 16 can be on a handheld, can be in a carrier, by Marines on a shore, by whatever. It's the universal and virtually universal comlink that sends data for NATO, for all the allies, for everybody. Not everybody, but obviously, but for a lot of our allies and the U.S. So the actual experience that they get is hugely enhanced by the combination of NERPAC, potentially, which is why the Space Force, and we have a question here about, do we expect phase 3 contracts in the near future? So Space Force funded us for a $1.2 million contract, which we just completed recently. And they recognized us as one of the top potentials of the various contracts that were funded, and they just awarded us a $776,000 extension. I wish, and that extension is enough, we hope, that will get us to a point where we're ready to. Oh, we lost him. Will get us to a point soon, within, we hope, 9 months, that's the plan, in which we can get to a phase 3. And a phase 3 is, talking about the phase 3. If we can get to a phase 3, that's the much bigger contracts, 5, 10, 20, depends how much they want to do initially. And then it could start with something like, okay, we're just going to put it on F-35s, Navy F-35s, and then we expand it out from there, whatever. We're working closely with L3Harris on it. They're hugely supportive. And we expect that we hope certainly that we'll be looking at a phase 3 sometime next year. That's the hope, plan, etc. We certainly have something they really want. And thanks to Admiral Becker, we're in conversations with a lot of other folks in various parts of especially the Navy, but other places too, generals, admirals, and so forth. We're getting a lot of visibility. People know who we are now. And so I see it as, a big opportunity for the future. So yeah, do we want to move on and just take a few questions? I think we can jump in.
Charles, if I could sort of add
By all
color
means.
to that, for those who are not familiar with what a phase 3 is, the Small Business Innovative Research Program is a program that is funded by the Small Business Administration to crank out the engine of economic security, which is small businesses, right? To help small businesses grow in this country. SBIRs come in 3 phases. The first one is kind of, let's think about this, and it winds up with studies and analyses. Phase 2 is more to, the old phrase would be bending metal, actually building something, a prototype, a system to try out, a test. But once a phase 3 has been awarded, and it's awarded through a competitive process, a phase 2, once a phase 2 contract has been awarded and had success, a phase 3 is a vehicle by which anybody else can put dollars from their appropriated programs into a contract and procure that capability without having to go through a competition, because that company has already been through a competition to win the phase 2. So what that means is there's an accelerated and a geometric acceleration in terms of revenue potential when you move from a phase 2 to somebody saying, I can use that to solve my problem over here, and they award a phase 3 contract. It's a big deal. It's a BFD, a big financial deal.
Yeah, absolutely. Boy, that's our dream is a phase 3. And phase 3, you're on the road. You've kind of made it.
Production.
Pardon me? Yeah, production. You're a made man, right? That's pretty cool. So just I'm happy to just with respect to, I'll jump in and answer a couple of these questions. So one is ASICs. So what is an ASIC? It's an application-specific integrated circuit. And what those are is it's a chip that's specially made for a specific purpose. It has circuitry that's specifically designed to maximize the capability of the chip to perform a particular function. And it might be something like translate voice into text or something, or specific thing. And so they're talking about, what about using an ASIC for NERPAC? And we had thought that would be our goal. The bad part about it is it takes about 2 years and about $20+ million to do that. So it's not a minor point, and we've always loved the idea of it. But what we've done is we've come up with an innovative new idea for how to address this, put an NERPAC on a chip. And so we now believe that we have moved past, we've streamlined the way NERPAC works so that it's not going to need floating point. Not needing floating point translates into you don't need all the power of an ASIC. And so what we can do, and you may want to do one anyway down the road and all that stuff, but the net is what we can do now is a much, much cheaper process, much faster, much cheaper to put it on what's called it's a kind of system on chip. That is to say, it's got all the stuff you need to run. But it's called a microcontroller. And a microcontroller it's got its own little CPU, it's got its own little memory, it's got its own little system thing, your ROMs and so forth. And you take your technology and you have to put it in assembly code and stuff, but you burn it into the ROM. And it becomes a software exercise rather than a hardware exercise, which means that instead of $20 million and multiple years, you can probably do it in under 6 months for 500,000 to 1 million. Throwing out a number, I won't guarantee that, but it's probably something like that. And so on that basis, we can definitely look at, a process whereby we can get it onto a chip, and then you can put in all kinds of things. You could put it into a little sensor, because the chip's cheap. It might be 10 cents or 20 cents or something. And so you can stick it into a sensor. You could stick it into whatever you like. So anyway, so that's the quick answer to that question. Harrison, feel free to ask another, whatever you like.
Sure. I'd like to maybe bridge something you and Admiral Becker both talked about relating to PCM, Charles. You talked about its ability to operate locally. And Admiral Becker, would love to get your opinion on that with rising concerns of reliance on foreign AI systems and cloud services. How important and powerful is it that PCM can operate locally while still benefiting from this federated learning that Charles talked about?
That's one of the things that makes it different. And being able to run on smaller form factors, being able to specialize and learn locally, at the risk of getting frustrated with any mathematicians on the line, I'll say it's kind of like a fractal approach, right? But I'm going to take that fractal and scale up. So I've got an in situ local instantiation of PCM running on a very economical, store and compute architecture with a very rapid developing understanding of my local environment. And then I scale that up. So put it in practical terms, let's start with a UXS, right? An unmanned surface vehicle. And now I'm talking about a number of those unmanned surface vehicles, or USVs. And now I'm going to connect to the surface ship that is the host for those USVs. So that fractal, I'm getting the bigger picture, right? Taking that mantle shape and growing out a little bit. And now I'm going to take that one surface ship and connect it to a squadron of surface ships each with its own cohort of USVs. And now I'm going to scale out to a strike group, right? And now I'm going to scale out from a strike group to a combined fleet. So you get the picture here. But each of those is an instantiation of PCM, all working with each other, all communicating with each other over protected links. Those links may in fact be improved and accelerated with technology like NURPAC, especially when I'm talking about the output of sensor data, not necessarily those sensor data themselves, but rather than taking an image of something and trying to pass an image, I can pass all the metadata about that image. Similarly, it was a question about network security, right? Instead of real time, passing the entire network infrastructure, if I have the metadata about that network, I can pass sensing data about the operation and security of that network. So I grow that fractal, again in air quotes, of understanding and knowledge and performance, and I haven't touched a data center anywhere except under the control of that architecture. If you turn the clock back to the 90s, there was this document. There was a leading document. It was a sort of a North Star for many things within the Department of Defense. Joint Vision 2010, right? What should the future look like? Joint Vision 2010. It was followed up by Joint Vision, any guesses? 2020, right? There was Joint Vision 2020. I don't think there was unlike, it's like Alien, right? The first movie's really great. The second one's really good. After that, So there was no Joint Vision 2030, but there have been visions since then. At the core of 2010, at the core of 2020, at the core of every vision since then has been something along the lines of ForceNet. And you can Google this up, right? What is ForceNet? It's the ability to connect. It's the ability to pass information, not necessarily in a hub and spoke, but throughout the pieces that make up the overall network. And so that terminology has gone from ForceNet into things like, instead of network, into webs, right? And into kill webs, and then from webs to meshes. Right now we talk about meshes. Well, that's exactly what we're talking about here with NURPAC being able to enable those webs, those meshes at speed, and PCM being the accelerant in the command and control cycle to preserve the information, the value of the information at the instant, to predict where that information may go, and then to present to the commander options, so that the commander's focusing their weapon system, the stuff between their ears, and what the futures could be, and shaping those futures for the good guys, and limiting those futures for the not good guys, rather than looking at displays and understanding, well, what was happening before? How can I react to what was happening? Maybe I could react to what was happening better now. What PCM enables, what NURPAC can lead to, can enable today, is what future do I want to happen, and how do I shape that future? And that, to go back to what I said earlier, that is the game changer, right? That is not the buzzword. That's for realsies, right? That is a game changer.
It's really powerful. Charles, two related questions from the audience for you. One, is the U.S. Navy's initial PCM utility test still scheduled for next month, given the sort of recent congressional budget issues we've seen? And then related to that, why choose to go the DoD government route first for PCM as opposed to the private side when that funding has been somewhat unreliable at times?
Right. No, it's a good question. So answer to the first one is yes. We have not actually set a time, but Admiral Becker and I were down at the command, what was it, last week? Or a week, I think it was last week. And we ran into the folks that are involved, and they're very enthusiastic, planning probably multiple sessions because they fill up the room. They absolutely want it to happen. We haven't formally scheduled it. We have a call with them tomorrow to do that. Now, the other question on why go PCM to DoD first, part of it was just because we had, thanks again, of course, to Admiral Becker, we had a discussion with these guys in depth. We had, we get a very high level of interest and support because of Admiral Becker's, reputation, position, and all that. So, we got, the top treatment there. And and part of it is we really want to, we think that, all right, so just to roll back. So who's going to pay for R&D? Commercial guys? DoD, as a matter of fact, yes. So going first to DoD is not only it's the right thing to do from support the nation perspective, but it's also really the only place where somebody's going to actually pay for R&D, at least until we get it to a level at which someone says, we better buy this thing, or we better put money in these guys, we better capture this technology somehow. So, we're not there yet in terms of like, okay, this is ready to roll out and start being used commercially. We have PhDs racing to make this real. And we've demonstrated that it works. That is to say, the core things work. But that's a lot different than here's something you can use and roll out to some commercial company. So that's the essence of it.
Going back to you, Admiral Becker, almost fast forwarding as you think about the context of the R&D timeline with the DoD, if you were to prioritize PCM NURPAC integration, how would you do that? Would you start on new platforms? Would you start with maybe retrofitting critical systems? Or would you focus on warfare areas, for example, ASW or missile defense? How would you approach that integration?
I'd start now, right? With systems that are in place, and with implementations that have the most straightforward implementation to make it as simple as possible for operations maintenance, for training, right? We want a capability that's going to change, well, let's put it in a metaphor for sports, right? If I'm going to start to teach a new play before a big game, I'm probably going to stay away from the triple reverse wishbone, ash can, whatever, right? Just try something simple but different. That's what I want to go with here, right? I want something that people can learn quickly and implement quickly because I want to upgun capability tomorrow. Then in parallel, as new systems are in different phases of acquisition, I would implement it there as well and sort of lead turn an implementation that was more sophisticated, an implementation that was more pervasive. And this would go both for PCM and for NURPAC, an implementation that was embedded in the very fabric of new capability. So as an example, right, what are we looking at in aviation? Sixth generation aircraft, CCAs, CC, what a perfect target for what we've been talking about here with both PCM and NURPAC, right? How would I change the data flowing between CCAs and host aircraft or motherships? Wow, I mean, that's a perfect use case. That's a very complicated use case, right? And a very heavy lift. So that's long term. Now, logistics, machinery control, data links that exist today that are ubiquitous, like Link 16, where I've got a small link already, and the kind of change and improvement that NURPAC could make would be huge, right? There are other links like that are available today to upgun with NURPAC that we could do tomorrow.
Great. So talk about really quickly, if I said, no, why don't we just change out Link 16 with a faster data link?
But once I stopped laughing, I would educate you on the complexities of changing anything that has to do with safety of flight, right? Anything that has to do with connecting a firing pulse to a weapon, anything that would have to do with physically changing hardware implementations in literally tens of thousands of devices across multiple services and coalition partners, right? That is complicated, but that's not NURPAC.
Right.
You change and implement NURPAC with a squirt of software into existing hardware today. There's no touch labor. I could back it out, and I could change it and implement it inside of existing encryption architectures, which is one of the biggest things you'd have to change if you said, I wanted to make a completely new data link. So that's why I chose.
See, I do that already. All right. I just was setting you up there.
Did you go to B school or law school?
Yeah.
Asking a question you know the answer to already.
Yep. Way ahead of you. Way ahead.
With a few minutes left here, there's sort of a bigger question for the audience that I want to get both of your guys' answers on. First part, how do you protect PCM from being reverse engineered by foreign entities? Second part of the question, what can be done? How do you handle the ethics behind what can be done with PCM? And I think that's a bigger question that people have asked about a lot of large language models. So we'd love to get both of your answers on those questions. Charles, maybe we'll start with you.
Okay. So yeah, on PCM, I got to tell you, we've had PhD mathematicians look at it and read the one of the white papers and still go, I don't get it. Right. And so I think it's going to be a little hard for somebody to figure this one out. It's just and not only that, people working on it are not PhDs in computer science, they're physicists. And so this is I'm not saying they couldn't figure it out, but I got to tell you, it's going to be intense. But at the same time, we went the patenting route. We're publishing patents. They get published. People can read them. we're trying not to do too much of the guts of how it's actually done versus this is what it is. But, I'm not saying it couldn't be copied, but they would have to infringe patents for that to be the case.
A loose metaphor, but a way to work in a great book, because I love books and I like to make a recommendation, is the application of a chronometer to determine longitude. All the smartest astronomers of the day were trying to figure out how to determine longitude in the 18th century, and they couldn't get it done, right? They didn't know how to do it. The person who figured it out was a clockmaker who came at it from a completely different direction. And that's what we have here, right? This is coming at an AI from a completely different direction. You might be able to read the patent about it. You might understand that you can tell time, you can tell longitude with a clock, but how to build that clock and how to do it, it's different. So that's kind of what we have here, just a wee bit. And the book is called Longitude. If you've ever heard of it, it's a wonderful little book. It's about that thick, but a great read.
I'd love to close with some parting thoughts from you guys. I think just generally speaking, any closing remarks you want to end with, but then more relating to our discussion and these specific applications of the two technologies we've talked about today. Why are NERPAC and PCM, what they're doing, so important for the Navy and the broader defense community?
If you would, don't mind, Charles, I'll start, and then I'll turn the talk over to you to finish up. These two technologies are important to our economic security and our national security. Atombeam is a company that is, I think, poised to deliver tremendous capabilities to partners and to those that would apply this technology to solving various problems. And that engine is a strong engine. And so I believe it contributes to the economic security and the national security in a variety of ways. I'm excited to see where this goes. I've been able to take a peek under the hood of both technologies, and that's why I'm here on the board, because I'd like to shape this company's future and contribute to it, because it can have such an impact on the mission of our economic security and supporting our national security.
Good. Yeah, thanks. So my thoughts are, one, there's a bunch of questions we didn't get answered. Apologies there. So Harrison, if you would send me those questions, I will do an update and answer them.
Absolutely.
Second thing is on sort of like, probably everybody watching this has already put money in, but the number I'm looking at it is 4,063,000. We cannot pass 5 million. It's not allowed. And so if you're interested in investing, do it soon, because the actual number is actually more, because StartEngine's site doesn't show some of the bigger investments because they have to clear through ACH and stuff. And so the actual number is higher. And so I'm just giving everybody fair warning, because I know what's going to happen, because this always happens to us. We get these big wait lists and people get frustrated, and I get emails and stuff. So I'm just saying to everyone here, and this isn't just, invest now, hooray. I'm saying, to avoid yelling at me, it would be great if you wouldn't mind going ahead and doing it now. Because I think, look, I mean, yeah, this is a lot higher valuation than last time, but I got to tell you, I mean, once the PCM in particular, once the NERPAC starts getting traction, and once PCM gets out there and people start understanding, we're already getting calls from major league big AI and hyperscalers and stuff, because they see the patents coming out. And so, I mean, and we're talking names, I mean, so my point is here is that this isn't going to stay on, it's got a lid on it right now, in part because we're being careful about who we talk to and what we say. But when the lid comes off, I don't think it's going to be, we're going to be looking at this valuation. That's my thing, my thought.
Well, thank you both, Admiral Becker and Charles, for joining. Thanks everyone who joined us to listen in. As Charles mentioned, you can invest and ask him questions at startengine.com/offering/Atombeam. They've raised over $4 million in the last 7 days, and today is actually the final day to earn 15% bonuses. That perk ends at 11:59 p.m. Pacific time this evening, so lock in those bonuses. You can learn more, and thanks everyone for joining. Charles, Admiral Becker, thank you both for your time.
Thanks, Harrison, and thanks, Admiral Becker.
Pleasure.